We will now start a new chapter, and this is the main topic of this course. So we will now start integration. So we will study how to define the Lebesgue integral of a measurable function over a measure space, and then study the properties of the integral, which we usually know for the Riemann integral. We'll try to see what are the different kinds of theorems which you can prove. Okay, so let x s mu be a measure space and phi from x to r a measurable function. Which is non-negative. Okay. So first we will look at non-negative simple functions. Let alpha I equal to 1 to n, the set of non-zero values assumed by phi. So we are taking a measurable simple function which is non-negative. So it takes only a finite number of values, being a simple function, and let us take ai to be equal to phi inverse of alpha I, 1 less than equal to I less than equal to n. Then ai are all measurable and mutually disjoint. And you can write phi as sigma I equals 1 to n alpha I chi of a. Okay, so in order to define the integral, we are going to imitate what we did in the case of the Riemann integral. So suppose you had a step function psi equals sigma alpha I equals 1 to n alpha I chi of I. So let us put j so that not too many i's around. Okay, where ij are the intervals in R, and then disjoint. Then how do you define the integral? The integral is nothing but the area under the curve. So integral psi of x dx over whatever over R, if you like, will be equal to sigma j equals 1 to n alpha j into the measure of ij. This is what we said in the preamble, namely we look at go along the y-axis and take an aerial view of the function and then measure it, and that is, it is to find the when instead of ij, if you had arbitrary sets, then what do you mean by measure of an arbitrary set? That's the reason why we define measure theory up to now. So imitating this, so we define, we set integral phi over the set x with respect to the measure mu. So integral of phi over x with respect to the measure mu. So this is the meaning of this symbol. So this we are going to define, if possible, as sigma I equals 1 to n alpha I measure of ai. Okay, now before we proceed further, we note that you can express a function which is a characteristic, a simple function, in more than one ways as a sum of characteristic, linear combination of characteristic functions. For instance, if I have chi of say minus 1 1 plus chi of 0 2, this can be written as chi of minus 1 0 plus chi of 0 1, then again 2 times this plus chi of 1 2. Okay, and these are disjoint. Of course, we can also write it in various other ways. So we want to know which way are we going to. So we can even write a function which is given in terms of disjoint sets, in terms of non-disjoint sets. So we would like to define the integral in a way that we are not worried about how the function has been, simple function has been written, whether it's so. If you write, for instance, so we can have many cases. One is phi can be written as a finite linear combination of disjoint sets of characteristic functions of disjoint sets in many ways. For instance, I can split this chi of 1 2 as chi of 1 3 by 2 plus chi of 3 by 2 2, for instance. So there are so many ways in which you can write, and even also phi can also be written in the form sigma j equals 1 to k gamma I ei gamma j ej, where ej not necessarily disjoint. Example is here, this is not disjoint, and so we would like to define the integral in a way which is independent of the way in which we write, because it will be difficult for us to break up the function each time according to the original form in which we wrote, and therefore we would like to give a more robust definition of the integral. So let us assume, so start with phi equals sigma I equals 1 to n alpha I ai, where ai is in fact phi inverse of alpha I. So this is the first form which you are taking. So now let us assume that this is equal to sigma j equals 1 to m beta j chi of bj, where bj j equals 1 to m are disjoint. So this is the first form, this is the second form. They are all disjoint, but they are not necessarily the level sets. Okay. So the third form is sigma I equals 1 to k gamma I chi of ei not necessarily disjoint. So this is the third form in which we are going to write a given function. Okay, so let us take, so phi as in 2. So this means phi equals sigma j equals 1 to m beta j chi of bj disjoint. Then each bj equal to alpha I for some 1 less than equal to I less than equal to n, and in this case Bj will be contained in Ai. So mu is finitely additive, and you have Ai is equal to the union over all j such that beta j equal to alpha I and Bj, because you can regroup according to the values, and therefore mu of Ai is equal to sigma over all j such that beta j equals alpha I mu of Bj. And now it immediately follows because of this that, so this now implies that sigma I equals 1 to n alpha I mu of Ai is the same as sigma j equals 1 to m beta j mu of Bj. Okay, from this it follows immediately. Okay, so now let us look at the third form, phi as in 3. That means phi equals sigma I equals 1 to k gamma I mu of Ei. So we want to show in this also we can write the integral as sigma gamma I chi of E mu of Ei. We want, right, to show that to show integral over x phi d mu, which is equal to sigma I equals 1 to n alpha I mu of Ai is equal to sigma I equals 1 to k gamma I mu of Ei. So it doesn't matter which way you write the function, the answer is always, integral is immediate to write. Once you are given a simple function, we can simply write it as the replay in this fashion. So this is the idea. So we have to prove this now. So let sigma equal to sigma 1 to sigma k, a k tuple. Sigma I equals plus minus 1 for each I. So E1 to Ek are the sets. So k is a set index which comes here, and for each I you have, and you put sigma 0 is the one which minus 1 minus 1 minus 1. Okay. Now we define E sigma as integral intersection I equals 1 to k of Ei sigma I. Okay, so Ei sigma I equals Ei if sigma I equal to plus 1, and Ei complement if sigma I equal to minus 1. So you take all these intersections and you define this. So you have E sigma naught, for instance, is equal to intersection I equals 1 to k of Ei complement, and that is equal to, of course, union I equals 1 to k Ei complement. So if sigma and sigma dash are two k tuples such that sigma is not equal to sigma dash, that means there exists an I 1 less than equal to I less than equal to k such that sigma I is not equal to sigma I dash. Okay, so without loss of generality, let us assume sigma I equals plus 1 and sigma I dash equal to minus 1. Then by definition, E sigma is contained in E I and E sigma dash is contained in Ei complement. So thus sigma not equal to sigma dash implies E sigma intersection E sigma dash is always empty. So they are always disjoint. So lemma with the preceding notations for each 1 less than equal to I less than equal to k, ei is the union of E sigma, where sigma is such that sigma I equal to plus 1. So you take all k tuples such that the ith coordinate equal to plus 1, take the corresponding E sigma, take the union, then ei will be equal to that union. So proof: if sigma I equal to plus 1, then E sigma is contained in ei. So it implies RHS is contained in ei. Okay. So now for the reverse part, we have to show ei is contained in this union. So let us take x in E sigma, ei. Define sigma as follows: sigma I equal to sigma j equal to plus 1 if x belongs to ej, equal to minus 1 if x belongs to ej complement. And this implies that sigma I will be equal to plus 1 because x is in ei and x belongs to E sigma. So this implies that ei is contained in union E sigma, sigma I equal to 1. Okay, and therefore you have the lemma is proved. So now let us assume phi is written as sigma I equals 1 to k gamma I chi of ei. Now chi of ei by this lemma is equal to union E sigma, and that's equal to sigma of sigma I equal to plus 1 chi of E sigma, because all the E sigmas are disjoint. Consequently, phi is equal to sigma I equals 1 to k gamma I sigma over all sigmas such that sigma I equal to plus 1 chi of E sigma, which I am now going to interchange the order of summation. So this is chi sigma not equal to sigma naught, because if it's sigma naught it's an E complement and that's phi is 0, so we are not worried about that. So then into sigma summation over all I such that sigma I equal to plus 1. Summation over I such that sigma I equal to plus 1. Okay, so this is I am interchanging the order of the, so gamma I E sigma chi of E sigma. But so this is another way of writing the function phi in terms of disjoint sets. So by 2, so this is in form 2. The beta j, okay. So you have that sigma I equals 1 to n alpha I mu of ai is equal to sigma over sigma not equal to sigma naught, sigma over all I, sigma I equal to plus 1, gamma I mu of E sigma. Again, I will interchange the order of summation. This is equal to summation I equals 1 to k gamma I sigma summation over all sigma such that sigma I equal to plus 1 mu of E sigma. But that by lemma is nothing but sigma I equals 1 to k gamma I mu of EI, since EI equal to union E sigma, so overall sigma I equal to plus 1 and E sigma's disjoint. So whatever form you write the definition, XS mu measure space and phi equal to sigma I equals 1 to k gamma I chi of EI, gamma I non-negative. Okay, then the Lebesgue integral over x of phi with respect to mu equals definition sigma I equals 1 to k gamma I mu of E. So this is the definition of the integral when you have a simple function which is non-negative. So remark, measure of EI can be infinite. So integral can be infinite, and this is why we need gamma I greater or equal to 0. If gamma I change sign and you have gamma I equals with mu EI positive and gamma I negative, I mean infinite, and gamma j is also mu ej is negative, infinite, and gamma j is negative, then you cannot add these numbers meaningfully. When you have two infinities with opposite signs, then you cannot add them. And therefore, so that we do not have any ambiguity in the thing, we use only non-negative functions to start with. Remark again. So let E be contained in X, measurable. So you define S of E is a sigma algebra set of all sets of the form A intersection E, A belongs to S. So this will give you a sigma algebra on E. And then mu equals mu restricted to E. So mu of so mu E, if you like, so mu E is nothing but the same measure. Okay, so you just mu equals mu restricted to E. So now if phi is a non-negative simple function, sigma I equals 1 to k gamma I chi of EI, gamma I non-negative, then what is phi restricted to E? It's nothing but sigma I equals 1 to k gamma I chi of EI intersection E. So integral of phi restricted to E over E with respect to mu restricted to E So we call this as integral over E phi d mu. So what is integral over E of phi d mu? This is nothing but sigma I equals 1 to k gamma I mu of EI intersection E. And this is nothing but the integral over x of phi into chi E d. So you can think of this as another definition of the integral. So it is just this thing here. Finally, phi psi simple non-negative and psi is less than or equal to phi. So then we write phi in the first form, sigma I equals 1 to n alpha I ai, okay, and psi equals sigma beta j chi of ai, chi of bj, so ai is phi inverse of alpha I and beta j bj equals psi inverse of beta j. And you have that beta j equal to alpha I for some I, this will imply that bj has to be contained in some ai for some I, and in that case beta j is less than or equal to alpha I. Okay, so this is how it can happen. So when you are written in terms of disjoint sets, then clearly it follows that integral over x phi d mu is bigger than or equal to integral over x of psi d. So you have the integral for the bigger function is bigger, just as you express in the case of area under the curve, the bigger function will have more area under the curve and so on. So these are some of the important things. So next we will have to extend from simple functions to other functions. Okay, so we will do that next.